Okay, so visualizing this irregularly shaped solid can be the trickiest part, right? But once we have a solid pictured, we can take a slice of it, a typical cross section, and if we can write a formula for the area of that cross section and rewrite it as a function of one variable, we can then integrate. We can integrate that area function across the range of possible slices and get the volume of the entire solid. You can think of this as being analogous to finding the volume of a loaf of bread by summing up the individual volumes of each slice. So the volume of the first slice plus the volume of the second slice plus the volume of the third slice together would eventually equal the volume of the entire loaf of bread. And that's really the key concept here. Okay, let's go ahead and take a look then at our picture. So we need to be able to visualize what the base of the solid looks like. It's a quarter circle with radius 1. So if we first draw our two-dimensional, that's our top view, like we did on the Monday before winter break, we could say, okay, so a quarter circle, right, is the base of the solid, and then the radius is 1, and cross sections sliced perpendicular to the base. So thwack perpendicular to the base are squares. And so if we were to consider. Right, if we were to consider a cross section of this paperweight, if we were to turn it to face us, it would be the shape of a square. So there's our cross section, and now we can try to visualize this one more time. Again, if we had a quarter circle is our base. Can't do it. I can't do it without shading over here too. It's going to bother me for the rest of the day. If we were to try and visualize in now 3 dimensions, an x, y, and z axis, what this shape would look like again if we took a cross section perpendicular to the base, it would be a square. So that would be kind of coming out of the page. I don't really like that. I can do better than that. I know it. I just gotta believe. So it would be coming up out of the page. There we go. And so that's our blue square. In each case, there's a cross section. All right. So now let's see if we can better visualize that with an animation. So let's go ahead and take a look. We want a cross section that is a square coming out of, okay, so here we go. It looks like right here, if we could consider, right, what this would look like, we have a quarter circle as the base of my solid. And look, cross sections taken perpendicular to the base are squares. If we were to turn any of these cross sections out and look at them, they'd be squares. So let's see if that helps at all. So we'll start. The base is a quarter of a circle of radius 1. I don't know if I need a tap to start this. There we go. And so we can think of each slice here as a little slab. A slab that's a square. Notice how the side lengths of the square are varying as we scoot along the solid. And if we could find, right, if we could find the volume of one of those square slabs, right, and then add up the volumes of each of those square slabs together, we'd be left with, voila, the volume of the entire solid. So does everybody kind of see the paperweight? That's the scheme? Okay. All right, let's go ahead and do it. So here we go. We're going to, let's see. We'll try one more time. There we go. So one more time, we've got our cross section. That's a circle. We already drew that, and so our area, a cross section rather, that's a square. So our area of our square cross section, all right, is given by the formula A equals S squared. A equals S squared. Now we're going to try and rewrite this formula as a function of one variable. And so what do? Well, we'll look at our space shape and our cross section and the base. And it looks like the base of our paperweight is a quarter circle, which it must adhere to the formula, right? X squared plus y squared equals radius squared, in this case 1. Therefore, this green curve, right, so when solved for y, must be given by the plus or minus square root of 1 minus x squared. In this case, we're just dealing with this positive arc from this quarter circle that's above the x-axis. And so let's go ahead and let our equation y then equal the square root of 1 minus x squared. we'll go ahead and draw my typical cross-sectional slice. And I need that side length, S, in my formula to be rewritten with x's. And so how does that formula root 1 minus x squared compare with the side length in my square? Well, it looks like that is exactly the side length in the square. Doesn't that represent the base of my square, the side length of my square? So that should be no problem. I'm going to do it one more time here. So, whack. Perfect. So there's my side length. There's my side length S in my formula. So we'll go ahead and rewrite that then as a formula. The formula A of x. A of x is given by side length squared. And we saw how the green curve was given by the square root of 1 minus x squared. Therefore, my side length S is square root of 1 minus x squared. And squared is side length squared. So did we do that right? And what is the square root of 1 minus x squared squared? Well, it'll just be 1 minus x squared, right? So this is my A of x formula. 1 minus x squared. Okay, there's my area formula. What do we do? Okay? All right, so let's go ahead and set up a definite integral that would yield the volume of that solid and then evaluate. So here we go. In general, we know the volume V of my solid is given by an integral from A to B, right? The range of x values for where I can take cross-sectional slices. If I integrate my area formula times my infinitely thin width of each slab, the square slabs that we looked at, each slice, each one of these products is the volume of one slice. And if I sum, right, all those individual small volumes up, I would get the volume of the resulting solid V. So let's go ahead and do that with our particular area function. Here we go. The range of possible slices spans from x equals 0 up until x equals 1. So my limits will be 0 to 1. My A of x formula is quantity 1 minus x squared. And we're integrating with respect to x. So we'll simply evaluate this exactly and algebraically in accordance with the fundamental theorem of calculus. We'll find an antiderivative function for my integrand function, 1 minus x squared, substitute in my upper limit, substitute in my lower limit, and subtract the two, just like we did back before break. So here we go. What's an antiderivative for my integrand function, 1 minus x squared? Be ready to share with the class. What's an antiderivative function for that? Brandon?
X minus x cubed over 3.
Absolutely, thank you. We'll go ahead and evaluate that at my upper limit 1, evaluate at my lower limit 0, right? Subtract and then get my final answer. So this ends up being not too bad. It looks like 1 minus 1/3. And then minus, evaluate at the lower limit, x equals 0. And for my x is just 0 all the way through, so that's an easy evaluation. So it looks like at the end of the day, when the dust settles, we get 1 minus 1/3 is just 2/3. Is that right? Just 2/3 cubic units? Awesome. What do you think? That crazy looking solid, right, has a nice, easy, computable volume of 2/3. Anna?
Do we need units?
No, unless we're given some physical context or
Okay.
description, like if we're dealing with the turbine on a rocket engine or something like that, then we might want to say cubic inches, but it would be cubic units,
Okay.
right, for a volume, for a space shape. Good question. Awesome. What other questions do you guys have about today's bar? Nikki?
You always use the positive square root.
Always use your original region. So if we've drawn our region here, right, then we would use the positive square root. But I notice other people drew a region in a different quadrant. Then, right, depending upon which quadrant your original region lies, you'd have to make sure that you use like that. But then you'd also have different limits of integration. So if we drew it down here, then our limits now would be -1 to 1 or to 0, and it'll take care of that. So absolutely. That's why we always want to draw our picture, right, in 2D, and then draw, right, a typical cross-section, and that'll help us choose, right, exactly how to keep that distance positive by using our same area strategy. Top curve minus bottom curve results in a positive quantity. right curve minus left curve results in a positive quantity, depending on if we're integrating with respect to x versus with respect to y. Meg?
So whether it's a quarter circle or a whole circle, does it matter? You still use that equation, x squared plus y squared equals 1 squared?
Yes. The difference in this is if we were dealing with a semicircular base, what would have been different with our integral? Well, now we would have integrated from -1 to +1, right? Or doubled my integral from 0 to 1 in order to get the volume of the entire solid. And that makes sense. If our original one had been a semicircular base, that would be twice my quarter circle base. So it would be twice the resulting volume. So absolutely, it all depends on our description. And since I already drew all this on the first page, I better just add this quickly so we still have it in our recording as our cross section. Other questions about it? So we have to be able to systematically find the volume of irregular shaped solids using cross sections. Today is no different. We're going to continue doing the same thing. It's just that most of our solids today are going to result from taking an original region and rotating it about some axis of rotation. So we're going to find volume of solids of revolution. It's still this exact same concept. We're still going to take known cross sections, right? And we're going to sum up the volumes of individual slices to get the entire volume of the solid. So we're doing the same thing as we did before break, which will be a nice review. Please keep in mind that we've got our test coming up. For us, it's going to be Tuesday, A day, because of, I'm trying to show you this, because of the 2-hour early release. And so on Moodle, right, since the beginning, we've had our test planned for Friday the 8th. However, because of the 2-hour early release on Friday A day, we're going to go ahead and do a little flip-flop. And so this time, because I want you to have the same amount of time as the B day classes, you're going to have your unit test on Tuesday, the 12th A day. And you're going to begin instead on that 2-hour early release day, instead of taking the test with a short amount of time. Instead, you're going to do the first day of Unit 6, which is exponential and logarithmic functions. And so in this way, both classes will still be on track when it gets to be the 13th, the following week. So we'll do a little flip-flop. There's good and bads to this. The good news is you'll get the full amount of time for your test, right? And I think that that's priority. You'll be doing some exponential and logarithmic functions day 1 before you're taking your test. However, this does include derivatives and antiderivatives, which you know is a big part of your Unit 5. So I don't think that it's necessarily going to hurt you. In any case, it's going to give you the weekend, right, to work and review, and so it's kind of giving you a little bit extra time. I think there's pros and cons that go along with it, but it'll keep both classes on the same schedule and ensure that you have the full length of time to take the test. And so that's what we're going to do to handle that 2-hour early release. I'd hate for you to not feel like you had an opportunity, right, to do your very best on the test because just because we wanted to keep the AB cycle the same. So I decided to add that and do the flip-flop. Then by the 13th, we'll all be back on track. All right, questions about our modified schedule then? Great, now let's scoot back again and give yourself credit for those you complete on our OTL number 10 out of 19. So our OTL number 10 was out of 19. Give yourself credit for those who completed, please. Pencil, divide, answer.
Yeah, that's a good word.
Make sure your name, first and last is on there. Divide, enter, multiply by 2, and box frame cans to score nice and big on top. Please round to the nearest half point. Go ahead and pass from back to front, please. Front rowers, make sure they're facing the same direction. Very good. Number 10, number 10. Great. Okay, ladies and gentlemen. So we've got our modified schedule. Again, this will allow for the 2-hour early release, right? It'll make sure that we then have a full block period in order to take your Unit 5 test. So once again, we're doing a flip-flop. On Friday, the 8th, 8A, you're going to do your first day of Unit 6, exponential logarithmic functions, which does include derivatives and antiderivatives. And so I think that'll still be good practice. And then you'll be taking the test on Tuesday, the 12th, 8A. B-Day classes are going to be taking on Monday. So both classes are going to get the weekend as we kind of get back in the swing of things and work and prepare. We've got to pull up all that prior knowledge from before break to make sure that you guys do well. To that end, I included the concept and skill guide as a handout for today. So we're not going to be referring to that today, but I wanted you to have it in advance so you had plenty of time to work and review, right? Because that Unit 5 test is coming up before you know it. Today, we're going to continue looking at solids, finding the volume of irregularly shaped solids. Today we're going to look at solids as a result from taking some region and rotating it about a given axis of rotation. I had planned on giving stamps for this, but you can see my interrobang, boom. Huh? Are we really going to do this for stamps? I think after our winter break, it's going to be more useful to talk about this together. And so we're not going to go ahead and do this for stamps. Disregard the 1D, 2F, and so on and so forth. We're going to take a look at these together. And we're also going to spread this into next class period. Next class period, we're going to continue working with solids of revolution. In this way, everybody will get enough practice with volume, right? Because of where winter break fell, I want to make sure that we're comfortable dealing with it. So we're still looking at 5-9 solids of revolution. But we're going to look at it together. So once again, this is not going to be an activity for stamps. We're going to look at these together so that we can make sure we're comfortable with our strategy. Okay, ladies and gentlemen, so let's go ahead and everybody find your 5-9 solids of revolution packet. We're going to look at these together. We're going to look at 4, maybe 5 together today, depending upon how the timing goes. And then we're going to continue working with some 3D animations that I found online as we work with solids of revolution. And then next class, we're going to continue from not just disk method like today, but to washer method. And so we will stretch this out now, volume over 3 days, to make sure everybody has a good foundation because it's one of the main applications of integral calculus. All right, let's consider an original region that is triangular in shape. And so what if we had an original region that was triangular in shape? It's got a height of 10 and a base radius of 5. And so if we were to take that triangle and connect it along the x-axis, right? We consider the solid that results upon rotation about the x-axis. Let's think about what shape results. And so let's go ahead and consider an original region that's triangular in nature. And if we had that original triangular region, I shade the original region so we can know what curve we're going to use, right, and what we're going to use for our equation. If we were to spin that about the x-axis, can you think about the solid that would be traced out? Well, I like to think of these as like our kind of Christmas decorations, right? When we had, or party decorations, right? If we take some original 2D region and we rotate it about an axis of rotation, we think about the space shape that's traced out. If we were to continue spinning that around some axis of rotation, we're getting a three-dimensional, right, solid, a three-dimensional space shape. Let's consider, right, an original region that was, like part of a semicircle, looks like truncated, but if we took that and we spun it around some axis of rotation, in this case a horizontal axis of rotation, and see the 3D space shape that results, right? In this case, it's like the football from that first activity. It kind of looks like that football shape. Well, what if we took this triangular region, bless you, and if we had a cool visual aid, right? And we could consider the space shape that it results upon rotating this about the x-axis. So I'm going to spin right here on spinning the axis of rotation of the x-axis, right? Can you picture the space shape that would be traced out? Yeah, what would it be, Hayden? It would be a cone, right? It would be a cone. So what we're going to try to do is draw that. Oh gosh, so if we took this original region, right, and we're going to try to draw it now on our paper, on our two-dimensional paper. If we spun that around, we consider what the resulting solid would look like. So we'd now be down here. And if we took a cross-section perpendicular to the axis of rotation, right, if we took a cross-section, I don't want that so big. If we took a cross-section perpendicular to the axis of rotation and turned it to face you, what shape would it be? Well, it would be a circle. Right? So again, we're still going to draw that cross-section. And we can see that this cross-section is a circle, and it's got that blue radius that we've already drawn in the picture. So our job is to, again, write a formula for the area of that typical cross-section. It's just in this case, when we're doing a solid revolution, right, our base shape for the area is always going to be a circle, or circular in nature, as we'll see when we deal with the Washer method too. So what's the area formula for a cross-section? Well, in general, it's pi r squared. So pi r squared is the formula for the area of my circle. Our job, again, is to rewrite this area formula as a function of one variable, so that I can integrate that area function across the range of possible slices and, voila, be left with the volume of the cell. So just like before, it's just now we're dealing with typically circular cross-sections as opposed to like the square from Bellwork. All right, so can we do that? Well, certainly. Our job is to write this original region, right, and that radius r as a function of x. So can we consider what the radius r will be given as a function of x? Well, in order to do that, we'd have to write a formula for that original slant line. So can we do that? Well, I think so. If the original triangular region, right, had height, that triangle was height 10 and base radius, what was it? 5, and so what would the slope of that line segment be that connects the top of the radius back to the axis of rotation? 1/2, right? It would be over 10 and up 5, so up 1 and over 2, so 1/2. So y equals 1/2 x then would be a formula that gives that boundary curve for my region. Hey, that's great news, because then my area formula, right, can be rewritten as an area function. My area function is going to be pi radius squared, and the radius is that blue line segment which connects top curve y equals 1/2 x down to bottom curve is y equals 0, so that's just 1/2 x. Is that it? So one more rewrite, just to make it look pretty. We could say a of x is given by pi times, and this would be 1/2 x, quantity squared would be x squared over 4. Is that right? Awesome. Let's go ahead and set up a definite integral then. So to find our volume, we will integrate our area function across the range of typical cross sections from A to B with respect to x. For us, that'll be the integral from, well, the first typical cross section could be sliced at the beginning of the region on the left-hand side would be x equals 0 up until the rightmost cross-sectional slice would be x equals 10. My area function is pi over 4x squared. And we'll integrate that with respect to x. To avoid tripping, I like to pull that constant out. Pi over 4 is just a constant. I like to pull that out front of my integral symbol. I'll leave it as a constant multiple. And then find an antiderivative for x squared, we know an antiderivative for x squared would be x cubed over 3. And we'll evaluate that antiderivative function from 0 to 10. So here we go. We'll put the pi over 4 out front so I don't trip on it. My upper limit all the way through would be 10 cubed over 3 would be 1,000 thirds. Minus my lower limit all the way through would be 0. So I'm getting carry the 9 square root of the inverse tangent. I'll leave it exact with the pi in there, so I get 250 pi over 3. Is that what you guys are getting? 250 pi over 3. Don't put the pi in your calculator. Leave it out so that we can still do math frac, right? And keep it exact. So we're getting 1,000 divided by 4 is 250 thirds, and then times the pi, and that would be cubic units. So 250 pi over 3. So there was less to draw and visualize because they already had given you the picture there, right? So what happens, right, if we have less? So let's consider a second one. So what's our second one ask us about? Consider the region bounded by the following lines. Y equals -1, y equals 3, x equals 2, and the y-axis. So everyone, this is where we have to pay attention to detail and make sure that we can clearly delineate the original region before we do the rotation. So that's why I'm doing the shading, right? That's why I'm taking the night class at UW-Baraboo Sauk County with the crosshatch shading, just so we can identify that region. Y equals -1, equals 2. So my original region spans from y equals So everybody seeing the original region there, just like a rectangle? Everybody getting the same original region? Jake? Oh, why is the one lower? Yeah, that's not gonna work very well, is it? You gonna do that? Dang it. Good try. It was a good try. No cigar. All right. So if we're going to take that original region and rotate it about the y-axis, can we picture the resulting solid? Well, gosh, it would be super cool if we had a rotating tool and a rectangle. And access to Mr. Willauer's shop in order to make it. So here we go, right? I'm going to stand with my flag, and I'll wave my flag because I don't mind. And we're going to go ahead and spin this around the y-axis and visualize the solid that's traced out. So can we picture that? Right? So what would the resulting space shape, right? What would it look like? A cylinder, right? A cylinder. Well, great. Because we know the volume formula for a cylinder, so we'll be able to check our answer. But the idea is we want to use the concept here, the concept of the calculus, so that we can then handle more complicated things. So let's go ahead and draw the arrow of rotation. So we're going to spin that around the y-axis, and then consider the resulting space shape. Let's do our best. See what that would look like. that'd be pretty soon if I could draw it like that. So I'm shading my original region, but then I'm trying to recreate it, right? In the space shape of the result. Thwack! If I took a slice perpendicular to the axis of rotation, now my slices are horizontal, right? If I'm perpendicular to my axis of rotation, no longer do I have a vertical slice like a book on a shelf, but now I've got a horizontal slice, more like a stack of coins, right? Always draw your radius, right, in the original region so that we know what boundary curve equations to use. So I'll go ahead and draw my original radius right there. Grab all this goodness. And if I were to take that cross-sectional slice and turn it out to face me, what would it look like? Well, gosh. It would look like a circle. It would look like a circle with that green radius that I've drawn. Everybody see it? All right, let's go ahead and write my area formula then for a circle. Well, my area formula for a circle is the same old pi r squared. The difference here is that my cross-sectional slices are horizontal. So does this look more like slices that are books on a shelf, on a bookshelf? Or do they look more like slices that are coins in a stack of coins? This is more like your hoards of gold coins and nuts in Gringotts, right? And so here we're doing a stack of coins. So we're not going to integrate from left to right with x values with respect to x. Instead, we'll integrate from bottom to top, right, with respect to y. So let's go ahead and rewrite my formula then. A of y that has y's in it because we'll integrate with respect to y, not a of x. So how can we write that? Well, a of y is going to be given by, let's see, what is this radius in terms of y? Well, it's still a constant. It's just that my curves will be solved for x. This is x equals 2. This is x equals 0. This is right curve x equals 2 minus left curve x equals 0 is 2, right? It's just 2. Well, how come I don't have a y in it? Well, does the radius of my cylinder vary as I move along from bottom to top? No, so it's always 2, right? So my a of y is just going to be pi radius squared, where my radius is the green distance 2. Yes? So why would we take the time, right, to do this with the calculus if it's just a cylinder? Just so we can practice our setup in a different way. We're now going from bottom to top to make sure we have the concept to extend it to more complicated shapes. So let's do one final rewrite. So a of y equals 4 pi. Is that right? 4 pi? All right. So we'll integrate to find volume. In this case, we're going to integrate from bottom y value c to top y value d. My area function, in this case, a of y with respect to y. Let's do it. That'll be the integral from, what's the least most y value of my cylinder? Negative 1 up until 3. My area formula is 4 pi. Then we're integrating with respect to y. Well, this is an easy antiderivative. 4 pi is just a constant. So the antiderivative from 4 pi would be 4 pi y. Just like the antiderivative for 2 with respect to x is 2x. Or the antiderivative of 11 thirds with respect to m is 11 thirds m. So this would simply be 4 pi y evaluated from negative 1 to 3. So I'm getting 4 pi times 3 is 12 pi minus 4 pi times negative 1 is negative 4 pi, which means I'm getting 16 pi. Are you guys getting 16 pi? How can we check, right, to see that our calculus method is correct? How can we check this? Riley?
We can plug in our radius cylinder volume equation.
And what's our cylinder volume formula?
H.
All right, let's try it. Let's try our pi r squared h. for cylinder with radius 2, this would be pi 2 squared times height would be what? 1, 2, 3, 4, is that right? And 2 squared is 4 times 4 is 16 times pi of 165. So big. It works, right? It works. And so we've done it the long, involved calculus way, using a shape that we know just so that we can check and build confidence for when it really gets exciting, like number 3. So what's going on in number 3? Well, in number 3, don't we have a parabolic region? So number 3, we've got the region bounded by y equals x squared, y equals 5, and the y-axis. Let's everybody go ahead and draw the original region in 2 dimensions, and then rotate that region about the axis of rotation and consider the space shape. So y equals x squared. Was it y equals 5? Yep. Okay, so we always want to shade our original region. That'll help keep our quantities positive. Okay, so I'm going to shade the original region. Then I'm going to group that. Oops, I don't want that. That wasn't very helpful. I don't want these bad boys in there. Or that. Pretty close. So about the, so we're going to spin that about the y-axis this time. What 3D shape would be formed? If only we had parabola. Gosh, that'd be cool. Okay, so if we took our original parabolic region, we can see that as the shaded part, right? And we spin that around the y-axis and consider the space shape that's spaced out. What shape would that be? It's called a paraboloid, right? It's called a paraboloid. This is our 3-dimensional parabola, which is fun to say, paraboloid, right? Just in case we get bored or running out of stuff to work on tonight, we guys just say paraboloid, right? Paraboloid, that's fun. And what we want to do is try and draw that now on our 2-dimensional paper. So how are we going to do that? Well, we could take a typical cross section, and you know that it would be a circle. So I'm going to try to add some 3 dimensions here. So it would look kind of like this. Sort of like the nose cone on an airplane. Whack. And I'm going to go ahead and do a red radius here so you can see this more easily. I'll do a red radius this time. And if we turn this out to face us, what's that going to look like? By golly, it's going to look like a circle again. Something in common? Well, all of our cross section, when we do a solid revolution, right, are going to be circular. What's the formula for the area of this cross-sectional slice? Well, it's A equals pi r squared. Again. Does this more closely resemble, right? Does this more closer resemble the books on a shelf, right? Books on a shelf, or do these slices more closely resemble a stack of coins? Yeah, a stack of coins, a vertical stack of coins. And so again, we're not going to integrate with respect to x, we're going to integrate with respect to y. We're going to make this a little infinite thin thickness there. There you go. There's a little coin slice, a circular slice, stacked on top of each other. Great. So our job then is not to write an area function a of x. Since my axis of rotation was vertical, our individual slices resemble a vertical stack of coins. We're going to integrate from bottom to top, that is, with respect to y. So let's not write an area function a of x. Let's write an area function a of y, right? Which is given by pi r squared, where our challenge is to write that radius, that red radius, in terms of y. So can we do that? Well, certainly. Let's go back to our original picture. Our original region that we shaded was bounded by the curves y equals x squared. The vertical line x equals 0, and the horizontal line y equals 5. Therefore, that radius of my circle would be given by right curve solved for x minus left curve solved for x. So could I solve this right boundary curve of my original region for x? Certainly. It would be x equals what? Yeah, it would be x equals plus or minus root y, and the right side would just be the positive root y, like Jake's already specified. And so we just need the positive root y then for the right side. Which is great news then, because if my radius is right curve is positive root y minus left curve is x equals 0, the x-axis, I'm sorry, the y-axis rather has the equation x equals 0, then my radius is just root y no matter where I draw that slice. So root y is my red radius. So my area formula, a of y, is given by pi y. Right? Isn't that just pi y? Which we could always add to our list along with paraboloid as fun things to say when you get bored, right? Tonight, take a break from your conference. So let's go ahead and set up my definite integral. So here we go. My volume V is given by the integral from bottommost y value of my original region is what? 0. The topmost y value? 5, good. A of y is pi y, and with respect to y. Gosh, these are easy antiderivatives, aren't they? So we'll pull my constant out front, pi, so I don't trip on it. An antiderivative for y with respect to y would be y squared over 2, and evaluate from 0 to 5. So I get $25 pi over 2. Survey says you are correct. Awesome. Bless you. What kinds of questions are you having about the first three? Anna.
So you know that you with respect to y when you rotate it around the y-axis, and then with respect to x when you rotate it around the x-axis.
Yes, and I would extend that even to include when I rotate it around any vertical axis, right? Whether it's the y-axis or x equals 2, right?
Yeah.
The resulting solid, if it has like a stack of coins, I'm integrating from bottom to top with respect to y. Yes. If it's spinning around a horizontal axis, like the x-axis, then I'll be integrating with respect to x. Slices will resemble books on a shelf. Yeah, absolutely. Good. All right, let's go ahead and try another one then. So 4, I think we have another parabolic region, don't we? So everybody, let's find 4. So consider the region bounded by the following. Y equals x minus 2 quantity squared, and y equals 4. Let's see if we can find that region. So here we go. Y equals x minus 2 quantity squared, and y equals 4. So y equals x minus 2 is my regular parent function, y equals x squared, but shifted to the right 2 steps. All right, so now my vertex would be at 2, 0, out 1, up 1, out 1, up 1, out 2, up 2 squared is 4. So it looks like we get this region. I'll show you the original region so I know where to draw my rectangle, my radius, or when I draw my circular cross section. And if we were to rotate this, about the line y equals 4, that's going to be different then. It's not one of the axes, right? So far we've just done about around the x-axis, around the y-axis. Now we're going to rotate about y equals 4. So what's that going to look like? Well, let's go ahead and see. I know you guys aren't surprised anymore because you know I have all the shapes, so I don't have to do the build-up anymore, so we'll go right to it. So here's our original parabola. Notice how this time the original region lies below the axis of rotation. So we're going to see how that comes into play when we set up our definite integral. Yeah, I know. Okay, so here we go. Here we've got our original parabolic region, it's shaded. Now we're going to spin it about the line y equals 4. So my axis of rotation is above the original region, and when I spin that around, right, can we visualize the shape that's traced out? Yeah, that's my, used up the big finish already. That's the football kind of shape. Everybody see that? All right. Let's go ahead and see if we can do that in 2 dimensions. Oh gosh. Yeah, totally worth it, Jake. Totally worth it. How come it's doing that? Not worth it.
Anyone's trying to align something? I'm not sure.
We're going to pretend that that is good. And even though it's not. And we're picturing, and a slice thwack. Oh, geez. That's tricky. Always draw your radius in the original shaded region. That way we'll ensure that the quantities are positive and not be using some ghost function for which we don't have the equation for or have to write one. So where do I want to draw my radius in this cross section? I want to draw it in my original shaded region. I'm going to draw right here. Guys, everybody see it? This is a big deal. So you want to make sure you're drawing your radius in the original shaded region. That way we don't have to make up equations of new curves, of ghost curves that weren't in our original region, okay? Everybody see that? So when we turn that out to face us, what does it look like? Surprise! Circle. A circle and the radius in this picture is green. And whose area formula is given by pi r squared. Do my slices align vertically like books on a bookshelf or horizontally like coins stacked up in a pile? Bookshelf. So am I going to integrate with respect to x or with respect to y? with respect to x. We're going to go ahead and take that loaf of bread that's sitting on the counter, right? And we're going to go ahead and integrate from left to right, counting up each slice's individual volume and adding it to our whole. All right, so here we go. Let's write an area function, then a of x. A of x will be given by pi times radius squared. Radius is in green. So our job is to write that radius with x's in it as a function of x. Can we do that? Well, certainly. To keep that green quantity positive, we need to rely on our strategies back from finding the area of irregular shaped regions. And we always kept those vertical distances positive by doing top curve solve for y minus bottom curve solve for y. What's my top curve solve for y? Y equals 4. Isn't that top boundary curve of my original region? That's what, again, why I'm shading it. And what's my bottom curve? My bottom boundary curve solve for y. Well, that's y equals what? What was that from the original? That was my x minus 2 quantity squared from the original. So the bottom curve is x minus 2 quantity squared. So can we keep that radius positive? You bet your boots we can. I need more space, I think. It'll be top curve 4 minus bottom curve x minus 2 quantity squared, and then all squared for my radius squared. Everybody see that? So we got pi, and then 4 minus x minus 2 quantity squared, all squared. There's our pi r squared. Now I'm going to simplify this to make an easier integrand expression, right, before I do it. So instead of having to worry about finding an antiderivative for this green mess, we'll go ahead and do some simplification first to make our antiderivative evaluation easier. So let's keep going. And let's rewrite our a of x again. This would be 4 minus x squared minus 4x plus 4, close, squared. So I went ahead and I FOILed the binomial x minus 2 quantity squared and got x squared minus 4x plus 4. I then combined like terms with the positive 4 in front and the subtraction of 4. So no constant term. And now we're going to square that again to get one final area function that's simpler to integrate. So what would we get when we FOIL this? We get x to the 4th and then minus 8x cubed, and then plus 16x squared. Is that what you guys are getting? Great. Let's not distribute the pi through. We're just going to pull it out in front when we find an antiderivative anyhow. So now we'll finally set up our volume integral. So let's go ahead and do that now. My volume v will be given by leftmost cross-sectional slice could occur at leftmost x value of my original region, which is shaded. What's that? X equals 0 up until x equals 4. Isn't this intersection point 2 comma 4? Nope, it's 2 comma 0, so 2 then 1, 2, 4. So it's 4 comma 4 is right there. So my x value here is 4. A of x is pi times quantity x to the 4th minus 8x cubed plus 16x squared with respect to x. All right, let's go ahead and find the antiderivative function for that. We'll put the pi out front. I'm going to use square brackets this time instead of just a straight thing. For my evaluation, here we go. X to the 5th over 5 minus 8x to the 4th over 4 is just, isn't that just 2x to the 4th? Plus 16/3 x cubed. We're gonna forego the gadget arm, keep the pi out front, don't trip on it. And here we go. 4 all the way through. Oh gosh. 4 to the 5th, are you serious? 216, 5, 8, 8, something? Math 9? What's that, 1024? Thank you, Adam. Five, 12. I'm using a calculator because I'm just doing, yeah, you guys getting it?
56/3.
What's that?
24/3.
Right here is what?
24.
1024? So anytime that you guys want to go to Math 9 or Math Frac is fine because the key is our setup. Once we get to the integrand function, then it's okay to go to the calculator depending upon which portion of the AP exam you're on, right? Calculator versus non-calc. And so either way, we could do that by hand if we had to, or we can Math Frac it, but leave the pi out. If you do the Math Frac, you need to leave the pi out because once you put the pi in, you'll never be able to turn it back into a fraction. It's now irrational. So I'm going to leave the pi out and do my original. Place. So I'm getting 512 pi over 15. 512, yes! That's pretty sweet. Okay. What questions then you guys have on number 4? So what we're going to do is we're going to pause, right? And we're going to hold off on our number 5, right? Our number 5, which is going to include the use of what we call not a circular cross section, but a washer cross section. There's going to be a hole in the middle, okay? And so I want to go ahead and make sure we have some 3D animation to do that as well. In the meantime, we're going to then take a look back at our note sheet, okay? So what I want you guys to do is go ahead and take a look then at our original day 11 note sheet. And let's go ahead and see if our 3D animation can help us visualize some of these shapes. So once again, we need to be able to draw the 2-dimensional original region, spin it around an axis of rotation predefined, and determine the space shapes volume, the results using definite integration. So here we go. Let's consider the region R bounded by the curves y equals the square root of x, y equals 0, and x equals 3. Everybody, let's go ahead and sketch the original base then. Everybody see our original region? So our original region here is kind of part of that root x function in between the x-axis up until x equals 3. If we were now to rotate this around the x-axis, that would be spinning around this axis of rotation. Could we consider the solid results? Well, doesn't this look kind of like the nose cone, right, on an airplane? So can you picture it? So this would be kind of like the nose cone on an airplane, right? Is that right? Okay. So let's go ahead and see if we can draw that. And the cross section taken perpendicular. Make sure you draw your radius in the original shaded region to keep it, ensure the quantities are positive. Okay, so let's go ahead and see an animation for that. So here we want a y equals square root of x, and we want to spin it. Let's see if this one works for us. So here we have our square root of x, and we're going from 0 to 3. So we can consider each individual slice. And this wire animation is so good, but we could see each one of those slices would be like a little cylindrical disc. If we were to pull that out, right, that would be our circular cross section, which we'll write an area formula for. I can't take it anymore. Let's see if we can get a better one. So maybe, is this one going to be better? Is this going to work? Didn't work. Do I need anything?
You could play.
I think we're okay. Shall I try this? Are we in trouble? We won't do it. All right. That's okay. I think we can visualize it pretty well. Let's go ahead and then write our cross-sectional formula. So we'll go ahead and turn that out to face us. And yes, it is a circle. I've drawn a green radius, so I'll draw a green radius. Our area then of that cross-section will be given by pi r squared. And again, will it make sense to integrate this with respect to x or with respect to y in this case? Anna?
X.
With respect to x. And so we'll go ahead and write an area formula then. It's a of x, not a of y. Pi radius squared. Or our radius is the green, that green line segment. How would I keep the green line segment positive? Easy. Look at your original region. Top curve solve for y minus bottom curve solve for y will ensure that that vertical distance remains positive. So the top curve solve for y is what? It's just square root of x. It's already solved for y, isn't it? Minus bottom curve solve for y. The x-axis is y equals 0. Therefore, my green radius is simply square root of x. Is that it? Awesome. So my area function a of x is pi x. All right, time for volume. My volume V then will be given by the integral from leftmost x value of my region would be 0 up until when? 3. My area function will be pi x. Integrating with respect to x will yield the volume. It looks like this is simply pi x squared over 2 from 0 to 3. So I'm getting 9 pi over 2, is that what you guys are getting? Yes! Okay, so I can't wait to, yeah, there you go. See, some of you have seen the trumpet already, so this is what I'm really super excited about. So what I want to do is go ahead and take a look at another one. So let's consider the region R bounded by the curves y equals x squared, y equals 0, and x equals 1. Let's find the volume of the solid when R is rotated about the x-axis. So everybody, let's go ahead and sketch my original region, shade that, and then let's rotate that original region about the x-axis and consider the three-dimensional space shape that results. So if we were to take that original region, bounded by y equals x squared, and x equals 1, and the y-axis, sorry, the x-axis rather, y equals 0, and spin it about the x-axis, we consider the solid that would result? Yeah, certainly. Don't worry, last one. It's all right. 2 ace bandages, 4 gauze pads, and 7 hours later, and voila, this little tiny visual aid. So we're going to spin it about the x-axis, right? And what results? Well, we got a cool one this time. Thank goodness. Thanks, Gophers. Oh no!
Block needs to be updated.
I go for some coffee. See that every time. Doesn't matter. Oh man. Oh, I don't know what to do. It's not gonna do it. It's not gonna do it. Okay, so all this does is it goes to this. Ooh, check it out. Except on mine, I can slide that circular cross section along it, so you can see that it's bigger if you go towards the edge of the, let's say, trumpet shape, and then it's a smaller circular disc if I go more towards the origin. Okay, so everybody turn it over. Voila. Right, everybody can see that, and now I've got that three-dimensional shape. So here it is. So when I go to that file, I can take this disc and I can slide it here and make a bigger circle versus a smaller circle to drive home the fact that's why we need an area function, because it changes depending upon where you're taking the slice. All right. In any case, we're ready to go. We can write an area formula there. I'm going to go ahead and take that circle on the screen and turn it to face me. By golly, that is a circular cross section, and it has a black radius. And we're going to write a formula for that circular cross section, and it's given by A equals pi r squared. Will we integrate with respect to x or with respect to y this time? Sophia? With respect to x, yep, from left to right. So let's go ahead and write an area formula then A of x. It has x's in it. So my A of x is going to be given by pi radius squared. But my radius, my black line segment radius is what distance? Well, what distance is it here? To keep that positive, we'll do top curve minus bottom curve. So that'd be y equals x squared minus y equals 0. So what's the radius of that circular cross section? X squared. And I'll write that in black. Pretty sweet. Which means that my area function that will integrate is a of x is given by pi x to the 4th. So the volume of that trumpet, right, of that trumpet-shaped solid, is given by integral from leftmost x value 0 up until rightmost x value 1 of pi x to the 4th with respect to x. That's it. Which means that my volume is given by pi x to the 5th over 5, evaluated from 0 to 1. Which in turn is pi over pi. How you feeling, Philly? Okay? All right. So let's go ahead and save. We're going to save this for washer method and washer method, and we'll do our general form. So to find volume, our general form using the disk method means that we have uniform circular cross sections. You guys don't have a closure on there? Oh, like it didn't come. That's all right. We can write this down. We can write this down. V equals. And it'll be my integral, right? My integral of my area function, a of x, with respect to x. It's just that in our disk method, what form does my area function always take on? Well, it always takes on a circular cross section, and so we always have pi r squared. And on multiple choice items on the AP exam, oftentimes you'll see this pi written out front of my integral symbol. And so you'll see the typical form for integrating using the disk method, where I have circular cross sections, is pi integral from a to b of r squared with respect to x or with respect to y. So that's our general form for the disk method. Awesome. Next class, we're going to go ahead and extend it to include the washer method, okay, the washer method. And I want to take this last couple of minutes here in class to point out that we now do have a Moodle post this week. There was no Moodle post over winter break, right? And so I sent out a couple of different things. I sent out a just a regular news forum, recent news that I hope you got with an email, and then also on the actual discussion forum, it said no Moodle post over break. So I hope that you enjoyed that time off and were able to have a wonderful winter break free from Moodle posts. But we do have one on area this week, and you're going to do exactly what we were doing last week, finding the area of an irregular shaped region. You're going to come up with the region, and your classmate's going to find its area. Awesome. So I'll go ahead and save the recording now. If you guys have a chance, then we'll get going on OTL number 11, and we'll look at the washer method next time.